This is a video lecture for Math 140 for Tuesday, April 28th. And the topic today is applications of the laws of sines and cosines. Okay, so the last few days classes we've been talking about the law of sines, and I've written it here. Sine of A over A equals sine of B over B. And we've also talked about the law of cosines, and that says that A squared equals B squared plus C squared minus 2BC cosine of angle A. Now there are two other versions of the law of cosines. We could apply this to the other two sides, so we basically switch A out for B and C. But basically this is a law of cosines. That's all you really need to know. Okay, in today's lecture we're going to consider a few different example problems where we applied the law of sines and cosines to real life problems. And the first example is a hiking example actually, and I like to hike, so this is close to my heart. So let's read this problem together. There's a group of hikers that are approaching the base of the mountain, and when they're 1,250 meters away, they measure the angle of elevation of the mountain to be 35 degrees. Now the angle of elevation is basically how high does the summit appear above the horizon. And then they hike to the base of the mountain, and when they reach the base of the mountain, they measure the slope to be 48 degrees. Okay, so before we ask ourselves any questions about this situation, I think it would be a good idea to draw a diagram of what we have here. So let's just draw this out. So let's suppose, and this is a bit of a ideal model. I mean, anyone who's hiked knows topography doesn't look exactly like this, but let's assume the land is perfectly flat, and then we have a perfectly conically shaped mountain. So when the hikers, I'll draw a small hiker here to indicate this. When the hikers are 1,250 meters away, okay, they measure the angle of elevation of this mountain to be 35 degrees. And I'm going to draw that, in blue to indicate that this is the angle of elevation. So basically they measure the angle between the summit of the mountain and the ground, the horizon, to be 35 degrees. So we know that angle is 35 degrees. And then they hike to the base of the mountain, and they measure the slope of the mountain to be 48 degrees. So the way I can indicate that is I can continue a dotted line that's perfectly flat. And what that means is the slope of the mountain is 48 degrees steep. So this angle is 48 degrees. In the first part of this problem, we'd like to find out, once the hikers reach the base, they're then going to hike up this mountain, okay? And what we want to find out is how far do they have to hike up the mountain? So total distance up the mountain. You know, how far do they have to hike from the base to the summit? What is that total distance? Okay, and by the way, this is, for any hikers out there, this is a very steep slope, and you'd be really hard-pressed to hike a 48-degree mountain. That'd be crazy steep. But for the sake of this problem, let's just assume it's 48 degrees. Okay, the first thing I'm going to do is I'm going to label, if you notice here we have a triangle, a non-right triangle here. I'm going to label this side as D. Okay, that's D. And I want to determine D. I want to determine how far do they have to hike up the mountain. Okay. Well, the first step here is I can figure out some other angles. Now, I know that the slope is 48 degrees. The question is, what is this angle right here? This angle is the supplement of the angle right here, right? Because these two angles have to add to 180. So this angle has to be 180 minus 48, which is 132 degrees. Okay, so we know that angle is 132 degrees. And then we can actually figure out this little thin, narrow angle up here. This angle is equal to 180 minus 35 minus 132 degrees, okay, which comes out to 13 degrees. So we know that this angle right here is 13 degrees. So now we've found all the angles of our triangle, and we'd like to determine this distance D. Well, at this point, we can use the law of sines to determine D. So I'm going to take D divided by, I haven't labeled these with A, B, and C. I haven't really labeled this much at all, but that's okay. I can still use the law of sines. So the idea here is D divided by the sine of the angle opposite to D, which is 35 degrees. So we get D divided by sine of 35 degrees. And now we actually know this angle side pair right here. So I can write this is equal to 1250 divided by sine of 13 degrees. So this is now we're applying the law of sines to this problem. So the theory is there's no new theory here today, but we're basically considering different real life applications. And I can now solve for D. If you solve for D, D will equal 1250 times sine of 35 degrees divided by sine of 13 degrees. And if you guys plug this in your calculator, you get 3187 meters. And so now this is the total distance the hikers will have to walk to reach the summit. Okay. Another question we can ask ourselves is, what's the height of the mountain? Anyone climbing a mountain likes to know what the height is. So what is the height of this mountain? Can we determine it? The answer is we can determine it. And to do that, what I'm going to do is I'm going to go to this summit here. I'm going to drop down a perpendicular here. It's H, okay? And create a right triangle. So now I have this original non-right triangle. Now I have this right triangle, and I have this whole right triangle here. But for answering this question, I'm interested in this right triangle right here, the smaller right triangle. We can actually figure out H because now I know D is 3187. That's 3187. Okay. And I know this angle is 48, so I can figure out H by using the sine function. So sine, I can write sine of 48 degrees is equal to the opposite side, which is H, over the hypotenuse, which is 3187. And now I can solve this for H. H equals 3187 times sine of 48 degrees. Okay. And now I can plug this in my calculator, and this comes out to 2368. And this is the height of our mountain. This 2368 meters is the height. So this is a good example of an application of the law of sines to a real life problem. Let's see. Why don't we, I'm going to do another problem with you guys, then I'll break the video after that. So let's do another problem. I'm going to erase this now. And the second problem we're going to do is a problem with trajectories, and this could apply to airplanes or cars, or any moving object. So let's consider a car that drives 70 miles due east, then turns and drives, then drives 50 miles at a heading of 30 degrees north of east. Okay, so we have a situation where a car drives 70 miles due east and then turns and drives 50 miles at a heading of 30 degrees north of east. Okay, the first thing, before we ask ourselves questions about this problem, I think it's a good idea to draw a diagram of this, to make a diagram. And so we can draw the first path the car drives for 70 miles due east. Okay, then it turns and it drives at 30 degrees north of east for a shorter distance of 50. Okay, and so we have these two legs of this trip. And then what I'm going to do is connect these two legs, if I can. Yes, that worked pretty well, to create a triangle. Now the other thing I know is this car, when it reaches this point, it turns 30 degrees north of east. So that means that this angle is 30 degrees because it turned 30 degrees north of its due east direction. And the first part of this problem is, how far did the car end up from the starting point? Okay, how far does the car end up from its starting point? Well, it started right here. It ended up right here. So hopefully you guys see what I'm really looking for here is I'm looking for the length of this side of this triangle. So I'm going to label this D. That's what I'm interested in. I'm interested in that distance from the starting point to the end point. And we certainly have a non-right triangle here. Now, we don't know any angles yet of this triangle, but in fact we do. We can figure out one of the angles very easily. If this angle is 30 degrees, this angle here is the supplement of that angle. And so this angle here, hopefully you guys see, this angle must be 150 degrees. It's the supplement of the 30 degree angle here. 180 minus 30 is 150. So now I know this angle, and now I have an SAS triangle, right? I know this side, this angle, and this side. So I can now solve for D using the law of cosines. So this is an application of the law of cosines. And now I can write D squared. So let's apply the law of cosines to side D. D squared equals the sum of the squares of the other two sides, 70 squared plus 50 squared, minus 2 times 70 times 50 times the cosine of 150 degrees. Okay, that's what I get. And now it's a matter of just doing the arithmetic here. D squared is equal to, this is 4,900 plus 2,500. If you guys plug this in your calculator, this third term here, you get 6,062 positive. Now what happened here? We have a negative sign here, but the cosine of 150 is also negative. So two negatives make a positive, which makes this third term a positive. If you add these all together, we get 13,462. And the final step here is to take a square root. If we take a square root of that number to find D, we get 116.0 miles. So it turns out this driver ends up 116 miles from the starting point. Another thing we're interested in here in this problem is our heading. So what is the final heading of this driver? And heading just means is stated as degrees north of east. If you think about it, if I was going somewhere away from you guys and I said, hey, I'm 150 miles away, would that pinpoint my location? Well, it wouldn't, because it would tell you how far away I am, but you have no idea what direction I am from your position. So to actually uniquely pinpoint a location of someone, you not only have to specify how far you end up from your starting point, but what is your heading, what angle or what heading are you at from your starting point, okay? Headings are specified as degrees north of east. So we want to figure out, relative to the starting point, what is the final heading of this driver, or how many degrees north of east does this driver end up from this starting point? Okay, well hopefully you guys see that angle, the angle that specifies the heading is simply this angle theta. So theta is our heading. It's the angle degrees north of east the driver ends up at. Okay, so how do we find this angle? Well, we can actually use the law of sines to find this angle. So we can write sine of theta divided by the length of the side opposite to the angle, which is 50. Okay, and that equals, now we know D is 116, right? Now we can use this angle side pair. So we can write this as sine of 150 divided by 116. Okay, and now we've used our law of sines, and we can solve for sine of theta. Sine of theta will equal 50 times sine of 150 divided by 116, which if you plug in your calculator comes out to 0.216. Okay, we're not quite done though, because we want the angle itself, not sine of the angle. And so the angle will equal the inverse sine of 0.216. If we take the inverse sine of that number, we get 12.4 degrees. And the way you would specify this is 12.4 degrees north of east. This is the final heading of this driver. It ends up 12.4 degrees north of east, ends up 116 miles from his starting point. That uniquely specifies his position. Okay, this concludes part 1 of this video lecture. In part 2, we'll do another example problem.